Today we're going to be talking about section 3.4. By the end of today, you will be able to define independent random variables, and you'll be able to apply formulas for variance, mean, etc., which hold for independent random variables. We already know that the expected value of x plus y is the expected value of x plus the expected value of y. But what about other operations? For instance, is the expected value of x times y equal to the expected value of x times the expected value of y? Unfortunately, that's not always true. However, there's something called independent random variables. Recall that events E and F are independent if the probability that E and F occur at the same time is equal to the probability of E times the probability of F. That's the same as saying that the probability of E given F is the probability of E, and the probability of F given E is the probability of F. Or in other words, it's the same as saying that the two events don't affect one another. For random variables, we have something similar. We say that random variables x and y are independent if for every two numbers a and b, the events x equals a and y equals b are independent. Think about this as saying that the two random variables don't affect one another. Knowing stuff about one, in other words, doesn't tell us anything about the other. Let's do an example. Consider the experiment: roll two six-sided dice with the random variables x equals to the number of sixes and y equals the sum of the two dice. Intuitively, these guys are not independent. Mathematically, we can see this by looking at, for instance, the event x equals 2. Well, if x equals 2, then we know that we have two sixes. But if we have two sixes, that means the sum of the two dice must be 12. And so, in other words, the probability that the sum of the two dice is 12, given that x is 2, is 1. On the other hand, there's only one way out of 36 to roll two dice and get a sum of 12. Since 1/36 is certainly not the same number as 1, the events x equals 2 and y equals 12 are not independent. They're dependent. And therefore, the random variables x and y themselves cannot be independent. Let's do another example. Draw a card from a standard deck, and with random variables x equal the number of spades and y equal to the number of kings. Are these independent? Note that the number of spades has values 0 or 1, since we're only drawing one card, and the number of kings has values 0 or 1, because again, we're only drawing one card. So let's try and put together some tables. So what we're going to try and do is fill in this table here, because we want to show that this, whatever we put here, is the same as whatever we put here, and whatever we put here is the same as whatever we put here. In other words, we want to show that this column and this column are the same. To help us do that, let's look at finding the PDFs for x and y. Well, the PDF for x, well, the probability that we have no spades, well, there are 39 cards which are not spades out of 52, so we have a 39 over 52 equals 3/4 probability of not getting a spade. And there are 13 spades out of 52 cards, so we have a 13 out of 52 equals 1/4 probability of getting a spade. Since there are 48 cards which are not kings out of 52, there are 12 out of 13 guys which are not kings. And so there's a 12 out of 13 probability of getting no kings. And so there's a 4 out of 52 chance or 1 in 13 chance of getting a king. Okay, so let's try and fill in this first row. Well, the probability of getting x equals 0 and y equals 0, so that means the probability that we have neither a spade nor a king. There are 36 cards which are neither spades nor kings out of a total of 52, so we have a 36 out of 52 chance. To get the stuff here, we just go look at the x equals 0 probability and multiply it by the y equals 0 probability. So that's 3/4 times 12/13, which is 36 over 52, and that's the same as what we got in the first column. So that's good. Let's look at the second row. The probability that x is 1 and y equals 0, well, there are 12 spades which are not a king, and so it's a 12 out of 52 probability. To get the last column over here, we look at where x is 1, so we have a 1/4 times where y is 0, 12 out of 13. So 1/4 times 12 out of 13 is 12 out of 52. Here, there are 3 cards which are a king but not a spade out of 52, so 3 out of 52 probability. And to get over here, we have 3/4, this 3/4 here, times 1/13 is 3 out of 52. And this last row, there's only one card which is both a spade and a king. And over here we have 1/4 times 1/13 is 152. 1/52, apologize. So looking at these two columns, they are the same, and therefore, yes indeed, the two random variables x and y are independent. Some formulas. If x and y are independent random variables, then the expected value of x times y, as we had hoped, is the expected value of x times the expected value of y. Moreover, the variance of x plus y is, in this case, the variance of x plus the variance of y. And if a and b are any real numbers, the variance of ax plus by is a squared, notice that squared there, times the variance of x plus b squared, so notice again that squared there, times the variance of y. Warning, if x and y are not independent, these formulas might not be true. Another property is that if x and y are independent random variables, then so are x squared and y squared.